Okay, so we want to show that this surface integral equals 0, where S is the boundary of the region enclosed by the cylinder y squared plus z squared equals 9, and the planes x equals 0 and x plus y equals 5. So first, I want to visualize this, so I drew this plot here. And so we have the cylinder on the yz plane with the radius equals 3, and then it goes from x equals 0 to the plane, which is x plus y equals 5. So in the xy plane, that's this line, and so in the z dimension it extends to the plane and it cuts off this cylinder here. So that's what it looks like. So we have three surfaces that we're working with: that top part, the bottom part, and then this side cylinder part. So let's just, so that surface integral, I didn't write this step, but maybe I should. It equals those three surfaces together. So take the first surface, the bottom part, x equals 0. X is in the function, so that automatically makes this 0 everywhere. Okay, so that was easy. And then let's do the next part. X plus y equals 5, the top part of the cylinder, the plane that cuts off the cylinder. So there are two different equations you can use to evaluate surface integrals. So this first one, you have an xyz function, then you put the third variable in terms of the first and second, so like you parameterize it with just these two variables, and then multiply it by the partial derivative with respect, well, the partial derivative of this third of z pretty much with respect to x and y, each squared, and then plus 1. So that, yeah, so you could look at this plus 1 as like a partial of g with respect to g. That's how I remember that. And then, so it's pretty much like the Pythagorean theorem in 3 dimensions. And then, so that turns into just a regular double integral instead of a surface integral. And then there's this other one that involves vectors, but for this one, I'm just going to use the first one. So z in terms of x and y, we're on the top plane, so the equation of that plane is x equals 5 minus y. But so instead of doing z in terms of x and y, actually here I'm doing x in terms of y and z. So pretty much you just move the y over and you have x in terms of y and z. So x is the variable that we're getting rid of because we are it's like we're projecting this surface here onto the YZ plane, pretty much. So, so plug that in for x here. You got 5 minus y, and then z. And then you're integrating over this region again. That's like the projection onto the YZ plane. And so the boundaries are going to be from the top half here to the bottom half. That's what z does. It goes from the bottom half to the top half, so top minus bottom. And then y goes from minus 3 to 3. We won't need it though. So if you take the partial derivative with respect to y, you're going to get minus 1, and then you square that. And then with respect to z, z's not in there, so it's 0. And then, well, you just have 1. That's part of the formula. So that's going to evaluate to square root of 2, but we won't need it because this integral is supposed to evaluate to 0. But it's here anyway. So let's integrate with respect to z first. So to find the bottom bound, we need the equation for this curve down here, and then the top bound is the equation of the curve up here. So that comes from the equation for the cylinder. So if you solve for z, because they're z values, they're z bounds, you get z equals plus or minus the square root of 9 minus y squared. So the plus part is the top half and the minus part is the bottom half. So you're going from minus that to positive that. When you integrate it, you get z squared over 2, and then because it's squared, it's going to make both of these positive. So you're pretty much just doing this squared minus the same thing squared. That makes it 0, just automatically. So that's pretty nice, because it means that our third integral is going to be 0 as well, because the whole thing has to equal 0. Alright, so the last part, the cylinder. For this one, let's use the vector parameterization. So pretty much just write the function in terms of the other variables. So we're going to do like cylindrical coordinates, but instead of regular cylindrical coordinates, I'm going to use theta in the YZ plane, because our cylinder is going in the x direction, which is just a coincidence of this problem. It could be going up and down, it doesn't matter. But so we're going to use these two parameters, theta and x, because those are the two that matter in the shape that we have here. Actually, we're just going along the very edge here. So r equals 3. So we don't need r as a parameter at all. We just need theta and x. So if we write this in terms of x and theta, the x direction, the x component, and the I hat direction is going to be just x. And then the y is going to be r sine theta, or no, r cosine theta, because it's this direction. And then z is going to be r sine theta. And so r is 3, and so we get that. So to find this Jacobian, I think it's called, it's the partial derivative of r with respect to one parameter crossed with partial with respect to the other. It doesn't matter the order because you're taking the magnitude. So the partial with respect to x, the only component that has an x in it is this one, so it's just going to be 1 I hat. And then with respect to theta, that has no theta, so it's 0, and so you just have the j component and the k component. So there's that and that. Yeah, so now let's take the cross product. So it's going to be ijk, and then 1, 0, 0, and then 0 minus 3 sine theta, positive 3 cosine theta. So if you take that, the first one would be I hat times 0 times that minus 0 times that, so that's 0. Then you have minus j hat times 1 times 3 cosine theta, and then minus 0. And then plus k hat times 1 minus 3 sine theta, or 1 times negative 3 sine theta. And then the opposite side, that's 0. Alright, so we just have that. So let's just take the magnitude from there, because we're going to be squaring and the signs will go all positive. So rx cross r theta, square root 9 cosine squared plus 9 sine squared, and because of the trig identity, sine squared plus cosine squared equals 1, that is going to equal 3. Okay, so now we can plug that into our equation here. So we're integrating along the cylinder. So theta is going to go from 0 to 2 pi, and then z, or I mean x, so the x direction, that's the one that's going to have a curve as one of the bounds, because it gets stopped by this plane that isn't just a constant x value. It varies with theta. So that's going to be our inner integral. So if you, well, x is a variable we're using, and z is going to be expressed, well, z here is going to have to be expressed in terms of x and theta. We just need theta though, because we already found that z is 3 sine theta. Okay, so just plug that in, And yeah, simplify it a little bit. Well, no, you take the integral of x first. And so that's going to be x squared over 2. Just pull out the 2 3's and the half, and you get 9 halves. The constants don't matter because it's going to be 0. But so sine theta, and then you have x squared. So there's the sine theta. And then x squared, you plug in the top bound, and then the bottom bound is 0, so you don't need to worry about that. But the top bound is squared. So if you look at this, if you look at the shape of cosine, it is symmetric around the midpoint of these bounds. So it's going to be the same to the left of theta equals pi as the right of theta equals pi. So you can see, so they're technically not even functions because it has to be symmetric around theta equals 0. I mean, this one happens to be, so it is even, but that's not why this will evaluate to 0, because our bounds have to be from minus a to plus a, so just the same value on both sides. And then sine theta, it's odd around, so it's anti-symmetric around theta equals pi, and so that makes this whole thing overall anti-symmetric over theta equals pi. But so if that's good enough for you, you can just say this is 0 because pi is the midpoint. But you could also just shift everything to the left if you don't want to go through the integral and solve it and find at the end it's going to be 0. You can still argue with symmetry that this is going to be 0 if you just shift everything to the left. So the bounds, just shift to the left by pi, and then plug theta plus pi in everywhere you see a theta, and that'll shift everything to the left. So yeah, so adding pi or shifting to the left, what it does to cosine theta is this the same as just flipping it upside down because it's periodic, and that's where it goes. So that's how much you have to shift it for it to be upside down, what it was originally. And then the same thing with sine theta. So you can factor out the negative from the sine theta, and then this just turns into a plus. And then these really are symmetric functions around the origin. This is an even function, and that's an odd function. And then now your bounds are also symmetric around the origin. So that means the answer is 0. Okay, so all three of the integrals, the surface integrals, added to 0. So that means that the overall surface integral is 0. Okay, so we showed that that was true. So if you have any questions, let me know. And hopefully I was clear enough explaining stuff. And hopefully I didn't make any algebra mistakes or anything. So just let me know if you find any. And yeah, thanks for watching.